Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and focuses on the orthogonal projection of a vector onto a subspace and the associated problems of orthogonal decomposition and distance. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. In this video, we're going to learn how to orthogonally project a vector onto a subspace. This is very similar to the orthogonal projection of a vector onto a line in R2, so I want to begin by reviewing this concept. In the previous video in this series, we learned how to project a vector y onto a vector u and a line through vector u and the origin. Since a line through the origin is a subspace, we were actually just projecting a vector onto a subspace. The orthogonal projection of y onto our subspace is our vector y hat, and the formula for y hat is given down here. Let's now look at the orthogonal projection of a vector in Rn onto a subspace. We're going to extend the concept of orthogonal projections onto a line L through the origin to projections onto a higher dimensional subspace W. We're going to be projecting vector y onto subspace W, where the set of vectors u1, u2, all the way up through up is any orthogonal basis of our subspace. Similar to what we saw above, the orthogonal projection of y onto our subspace W is y hat, and that formula is given right here. Notice that this formula has the same basic structure as the formula for the orthogonal projection of a vector onto a line. I also want to make a note that the number of terms in this formula is the same as the number of vectors in the orthogonal basis. Once we use this formula to find y hat, we can decompose y into its orthogonal components y hat and z. Y hat is the vector in the subspace W, and vector z, up here at the top, is the vector orthogonal to subspace W. Before we look at an example, I want to point out that when finding an orthogonal projection onto a subspace W, we must use an orthogonal basis for W. If the basis vectors are not orthogonal, the overlap in the vectors will lead to an error in the computation of the projection. Let's now look at an example where we're going to find the orthogonal projection of a vector y onto the xy plane. On the right, I've drawn vector y and what its projection onto the xy plane looks like. The first thing we need to do is we need to find an orthogonal basis for the xy plane. Our orthogonal basis is just going to be our standard basis vectors e1 and e2. E1 is the vector 1, 0, 0, because we're in R3, and then E2 is our vector 0, 1, 0. The formula for y hat is equal to y dotted with our first basis vector E1 divided by E1 dot E1 times E1 plus y dotted with E2 divided by E2 dot E2 times E2. Y hat is then equal to y dotted with E1, which is 2. E1 dotted with E1 is 1 times E1 plus y dotted with E2, which is going to be 4 divided by E2 dotted with E2, which is again 1, times E2. This gives us an answer for y hat that's the vector 2, 4, 0. Notice that the third component is equal to 0 since y hat lies on the xy plane and z is 0. Now that we understand this concept a little bit better, we can think about what it would be like if we projected y onto the xz plane. If we did that, our y hat would just be equal to 2, 0, 3, because our y component would be equal to 0. We could then find a similar vector for projecting y onto the yz plane. Let's now look at another example. In this example, we're given that W is the subspace spanned by vectors u1 and u2. Let's notice that the dot product of u1 and u2 is equal to 0, so that means that u1 and u2 form an orthogonal basis for W. The first part of this problem has us find the orthogonal projection of y onto our subspace W. Let's write down our formula. The projection we're going to call y hat, and it's going to be equal to y dotted with u1 divided by u1 dot u1 times u1 plus y dotted with u2 divided by u2 dot u2 times u2. Let's go ahead and compute this. So y hat is y dotted with u1. That's going to be a -1 plus 4 plus 3. We're just multiplying the corresponding components. And then u1 dotted with u1, we have to square each component of u1. So that's going to be 1 plus 1 plus 1. And this gets multiplied by u1. Let's now compute our y dotted with u2. Y dotted with u2 is going to be a 1 plus 12 minus 6, all divided by a 1 plus 9 plus 4. That's just u2 dotted with itself times u2. Our y hat is then going to be a 6 over 3 times u1 plus a 7 over 14 times u2. This is going to be equal to 2 times u1, which is the vector 1, 1, 1, plus 1/2 times u2, which is the vector -1, 3, -2. This gives us the vector 2 minus 1/2, which is 3/2, 2 plus 3/2, which is 7/2, and then 2 minus 1, which is 1. This vector then is the orthogonal projection of y onto our subspace W. For part B, we're going to write our vector y as the sum of a vector in W and a vector orthogonal to W. Our vector y is going to be y hat, that's the vector in W, plus a vector z, which is our vector that's going to be orthogonal to W. Since we were given vector y, and we just computed vector y hat, we can find vector z by subtracting vector y hat from vector y. So we have z is equal to y minus y hat. Let's go ahead and compute that. Our vector z is our vector y, which is our vector -1, 4, 3, minus y hat, that's the vector that we just computed, and that's 3/2, 7/2, and 1. Our vector z is then equal to -5/2, 1/2, and then 2. For our final answer, we're going to take our vector y and we're going to write it as the sum of a vector in W. That's our vector y hat, which is 3/2, 7/2, and 1, plus a vector orthogonal to W, which is our vector z, and that's -5/2, 1/2, and 2. I was talking with my students about a built-in check that you can use to see if some of these computations are correct. And one built-in check you can do is you can take vector y hat and you can dot it with vector z, and you can make sure that it's equal to 0 because those two vectors are orthogonal. Let's now learn how to find the closest point in a subspace to a vector in Rn. In the diagram below, the closest point in subspace W to vector y is going to be the point where vector y is projected orthogonally down onto our subspace. This point is called the closest point to y in subspace W, and it's also called the best approximation to y by vectors in W or vectors in the span of u1, u2, all the way up through up. This closest point or best approximation is just our vector y hat, and the formula for y hat is given here. Let's now walk through an example where we're going to find the closest point to vector y, there's our vector y, in the subspace W spanned by vectors u1 and u2. Note that this is the same thing as finding the best approximation to y by vectors in the span of u1 and u2. We're going to call the closest point to y, y hat, and it's given by this formula. You take y and you dot it with u1, and you divide that by u1 dot u1 times vector u1 plus y dotted with u2 times u2 dotted with u2 times u2. Let's now compute these dot products. Our y hat is y dotted with u1, so we're just going to multiply the same corresponding components. So this gives us a 6 plus 7 minus 6 plus 3. And then u1 dotted with u1, we just have to square each of the components in u1. So this is a 4 plus 1 plus 9 plus 1. Now let's do our next dot products. Y dotted with u2 is going to be 3 minus 7 plus 0 minus 3. And then the denominator, we're going to end up with u2 dotted with u2, so that's a 1 plus 1 plus 0 plus 1. Now let's go ahead and add all these numbers up. Up top, we're going to get a 10 over 15 times u1. And then over on the right, we're going to have a minus 7 over 3 times u2. Let's go ahead and write that 10 divided by 15 is going to be 2/3. So we have 2/3 u1 minus 7/3 u2. Now we can go ahead and write down what u1 and u2 are. So we have a 2/3 times our u1, which is 2 minus 1 minus 3, 1, minus our 7/3 times our u2, which is 1, 1, 0, minus 1. If we add these two vectors up, we're going to get a 4/3 minus 7/3, and then a minus 2/3 minus 7/3. And then we get a minus 2 minus 0. And then for our last component, we have 2/3 plus 7/3. If we add these fractions, we end up with the answer minus 1, minus 9/3, which is a minus 3, a minus 2, and then a 9/3, which is equal to 3. This vector, then, is the closest point to y in our subspace W. The last concept that we're going to look at is how to find the distance from a vector in Rn to a subspace. In the diagram below, we have a subspace W, and then we have our vector in Rn that's out of our subspace. And what we want to do is we want to find the distance, that's this distance right here, from our vector to our subspace W. The distance from vector y to our subspace W is the distance from y to the orthogonal projection of y onto subspace W, which is y hat. This distance is equal to the magnitude of y minus y hat. Let's walk through an example where we're going to find the distance from our vector y to the subspace of R4 spanned by vectors u1 and u2. Let's begin by writing down our formulas. Our distance is going to be the magnitude of y minus a vector that we'll call y hat, and y hat is going to be equal to y dotted with u1 dot u1 times u1 plus y dotted with u2 divided by u2 dot u2 times u2. Y hat is just the orthogonal projection of y onto our subspace. I think it's easiest if we break up this problem into 3 steps. So our first step is to find y hat. Let's go ahead and do that. So our y hat is going to be y dotted with u1. So that's going to be a 3 plus 2 minus 1 plus 26. And on the denominator, we have u1 dotted with itself. So we're just going to square each component, and we get a 1 plus 4 plus 1 plus 4. And that gets multiplied by u1. And then let's compute these next dot products. Y dotted with u2 is going to be minus 12 minus 1 plus 0 plus 39. And in the denominator, we have u2 dotted with u2. So that's going to be a 16 plus 1 plus 0 plus 9. And that multiplies vector u2. Let's now add up all these numbers. We're going to get on the top, let's see, we have a 5 minus 1, so that's a 4 plus 26 gives us a 30. And then down below, we have a 10. So that's nice. That's just 3 times u1. And then this next one, we're going to have a minus 13 plus 39. That's going to give us a 26. And then in the denominator, oh, this is nice. We also get a 26. And that multiplies by u2. So this is just 3 times u1 plus u2. Let's now go ahead and compute what that is. We're going to have to pull this down so we can look at our vectors again. We have 3 times u1. So that's going to be a 3 plus u2, so that's a minus 4. And then we're going to get a minus 6 plus 1. We're going to get a minus 3 plus 0. And then for the last component, we're going to get a 6 plus 3. We'll pull this up and give us a little bit more room. So our y hat is equal to minus 1, minus 5, minus 3, and 9. The second step that we're going to do is we're going to find y minus y hat. I always think it's easier if we do that in-between step before we calculate the magnitude. So y minus y hat is going to be our vector y. Let's look back up. 3 minus 1, 113. Minus y hat, that's what we just computed. Minus 1, minus 5, minus 3, and 9. And this gives us the vector 4, 4, 4. Oh, look, they're all 4s. That's going to make it nice to compute the magnitude. So that's our last step. We're going to compute the magnitude of y minus y hat. So to compute the magnitude, all we're going to do is we're going to square all the components in y minus y hat and then take the square root. So 4 squared is 16 plus 16 plus 16 plus 16. We have 4 of those, and that's the square root of 64. So we actually end up with a nice number of 8. the distance from Y to the subspace of R4 spanned by U1 and U2 is just equal to 8. Be sure to check out the next video in this series where I'll teach you all about the Gram-Schmidt process and QR factorization.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.